I want to hear from you all about parsecs, because this is one of these great classic old-time nerd discussions about Star Wars. When Han Solo brags about how fast and cool the Millennium Falcon is, he says that it made the Kessel Run. Apparently this is some route through space or something. It made the Kessel Run in less than 12 parsecs. He's bragging about his ship, right? Why do nerds argue about this? Or why would we take issue with a statement like it made the Kessel Run in less than 12 parsecs? Yeah, it's making it sound like he's saying that the ship is fast because it made the Kessel Run in only 12 hours or 12 minutes or something like that. It makes it sound like a parsec is a unit of time, when in fact, what is a parsec according to the work that you just did? What is it a unit of? Space, distance, length, right? Length. So I think people have tried in the past, and I don't know whether this was what was intended originally in the script, but people have tried to go back and say, well, he was really saying that he found some route in between stars and asteroids or whatever that was shorter than the routes that everybody else was able to find. And so, okay, it's fine to have a unit of distance there, but as was said in this group, it'd be like saying, oh, I have class in 5 meters. What? That doesn't make sense. Don't worry, we'll get lunch in like 3 feet or so. It's not that far away. Anyway, but I'm interested in parsec still, because the point of this question was to take the definition of a parsec, and the definition of a parsec is it's how far away from our solar system that you would have to be as an observer in order to look at the Earth and look at the Sun, and that there only be an angle of 1 arc-second in between the Earth and the Sun. So here we are out here somewhere in space, us, looking at the Earth and looking at the Sun, and there's only an angle of 1 arc-second that separates them from our viewpoint. Okay? And I want to know, how many miles are there in a parsec? So groups that wrote up this question, what did you do first? Because there were 2 different ways of approaching this problem. The Part A approach used right triangle trigonometry, and the Part B approach used arc length. So I think I gave this write-up problem to 2 different groups. So one group, tell me about the right triangle method. What did you do to unravel the distance of a parsec using right triangle trigonometry? Yeah.
Converted the parsec to degrees.
Okay, so no matter which group you were in, you had to do that part. Convert your arc seconds into an angle you can actually put into your calculator, either degrees or radians. So what's the conversion factor from arc seconds to degrees?
1 degree is 1 degree over 3,600 arc seconds.
There we go. 1 degree is 3,600 arc seconds. And so we have an angle of 1 over 3,600 degrees. So it's a teeny tiny little angle. And now that we have that angle, if we're thinking of this as a right triangle problem, what did you do then? This is part A. Yep.
You converted the atomic unit into meters.
Okay.
I converted it.
Either meters or miles, whatever you like. Let's imagine we converted it into miles, and we got the 92,900,000 and something thousand. I think it's something like this times 10 to the 7? No, 6 miles. Roughly 93 million. Whoops, 10 to the 7th. I had it right the first time. 10 to the 7th. All right, so again, no matter which approach you took to this problem, at some point you had to convert from atomic units, astronomical units rather, into meters or miles. Okay, so let's convert it into miles. We get something like 93 million. All right, but what's the right triangle approach? How did you find the length of a parsec using right triangle trigonometry?
To the distance of the AU, which was, we said 9.299 times 10 to the 7th miles, and put that over x, which x would be a variable for finding out the distance of 1 parsec.
Okay, so you're saying tangent here, and x is what you're calling the length of a parsec, and you took the tangent of this angle, 1 over 3,600. And so it means that you're imagining that this is a right triangle, and where is the right angle in this triangle? Us, Earth, or Sun? Yeah. Well, the way that this diagram is written, we're kind of imagining there to be a right angle down at the Sun. And then, because we have two lengths labeled on this right triangle, we have the opposite and the adjacent both labeled. Then the trig function that we need that relates opposite to adjacent is the tangent. So the tangent of 1 over 3600 degrees is the length of the opposite side, which is our 93 million miles, divided by x, which is the length of a parsec, and now the job is to solve this equation for x. So how do you get x by itself in this equation?
Well, first you have to multiply both sides by x. So x is
Okay.
the denominator anymore.
Great, so multiply both sides by x so that x is no longer trapped down in a denominator.
And then you're going to have to divide 9.299 times 10 to the 7th by tangent of 1 over 3,600.
Okay, great. So dividing both sides by the tangent of 1 over 3600 degrees, x is going to be 9.299 times 10 to the 7th miles, divided by the tangent of 1 over 3600 degrees. That tangent is something you can do on your calculator. Again, making sure this time your calculator is in degree mode, because that's the units that we have our angle expressed in. And what did you get? Doing it the right triangle way, what does this come out to be? How many miles in a parsec using the right triangle method? 1.918 times 10 to the 13th, and that's miles, right? Great. So dimensionally, that's about 19.2 trillion miles in a parsec. By the way, if you just take the tangent of 1 over 3600, how big is that number? Pretty small. Okay. Give it to me to 4 significant figures if you got it.
4.848 times 10 to the -6.
Times 10 to the -6. Yeah, teeny tiny. So when I take the tangent of a really tiny angle, I get a really tiny number, a number really, really close to 0. Which is why when we divide 93 million miles by that tangent, we're dividing a huge number by a tiny number, we get a massive number, 19.2 trillion miles. So that's the right triangle method. But what's the limitation of the right triangle method? If we're using the right triangle method, as I was saying to your group over here, we're kind of making the assumption that, well, the length of this side is 1 parsec. If we're thinking of this as a right triangle, we would be saying that this length, the hypotenuse of our right triangle, would have to then be more than 1 parsec. And that may or may not actually be an accurate assumption, depending on where we're standing in the galaxy to take this measurement. It's probably more likely that we would make the assumption that us as observers, because we're so far away, we're 19 trillion miles away from the Earth and the Sun, right, in this particular diagram. We're so far away from the Earth and the Sun that we might as well just make the assumption that we are the same distance away from the Earth as we are from the Sun. In other words, we don't want to play favorites between Earth and Sun, even though Earth happens to be my favorite of that pair. Rather than playing favorites, let's make the assumption that we are also a parsec away from Earth, and that's where part B comes in. So instead of thinking of this as a right triangle, we're going to think of it as an arc length question by making the assumption that both of these sides are 1 parsec in length. So now this is no longer a right triangle, but it's either, we can think of it as an isosceles triangle, if we're so inclined, or we can think of the distance between Earth and Sun as an arc of a circle, which is what's meant by an arc length. And if we do it that way, what do we have to do differently to compute an arc length instead? How do you find the length of an arc in trigonometry? Yeah, r times theta, the radius times the angle will give you the arc length. And so what's the radius in this example? Right, the radius is this thing that I don't know. That's equal to 1 parsec. What's the arc length in this problem? The s, if you like. length of this side. That's a piece of information we also had, 1 AU. So 1 AU is our arc length. And our angle, 1 arc second, or 1 over 3,600 degrees. But there's a problem with using that number. What's the problem? Before we can do an arc length calculation, our angle has to be in radian measure, not degree measure. So before we use this formula, we have to convert from degrees to radians. What's the conversion factor from degrees to radians? Right, yeah. Pi radians is how many degrees?
What's that?
How many degrees are in pi radians?
180.
180. So multiply by pi radians over 180 degrees, and we'll get an angle measured in radians. So 180 times 3,600. So our angle when measured in radians is pi over 648,000. Now I can drop that into my equation, 48,000. And so r, our unknown distance, how do we get that r by itself in this equation? Well, we need to get the 648,000 multiplied over to the other side, and the pi we would have to divide to the other side. So r is equal to 1 AU times 648,000 divided by pi. And again, since 1 AU is 9.299 times 10 to the 7th miles, multiply that by 648,000, divide it by pi, and make some room here. What comes out? Ask your calculator what this is. It tells you 1.918, at least to 4 significant figures, times 10 to the 13th miles. So what's interesting about this problem? Why did I have you do this in both ways? Right, what's the connection? They were equal, at least to the significance that we're using for our course, 4 significant figures. Both of these methods gave us the same answer. That will not always happen. In other words, we can't just get away with throwing away trigonometry altogether because both of these methods are going to give us the same thing. Okay. That only happened because why? Anyone know why these two answers are allowed to be so close together when we're measuring the length of a parsec? It didn't matter, in other words, whether we made this figure a right triangle or whether we made it an arc of a circle. Why not? Why are they so close? The distances are so vast, specifically the distance of 1 parsec, how far away we are from the solar system in taking this measurement, it's really large compared to what distance? Well, it's large compared to a mile. It's also even large compared to 1 AU, the distance between us and the sun. After all, how many orders of magnitude separate the distance, roughly how many orders of magnitude separate the distance of Earth to sun, 1 AU, from 1 parsec? Yeah, roughly like 6 orders of magnitude. So because that's such a huge difference, so 1 AU versus 1 parsec is roughly 6 orders of magnitude. In other words, it takes at least 1 million AUs to give us a parsec. Because that distance is so vast, it didn't matter whether we made that a right angle or whether we made this an arc of a circle. Another way to say that is that this angle, 1 arc second, 1 over 3,600 degrees, that angle is so tiny that it didn't really matter whether we considered this to be a right triangle or whether we considered it to be an arc. Because, here's something for you to play around with. This angle, 648,000, pi over 648,000 in radians, pi over 648,000. This is our angle measure in radians. Compare that to its own tangent, and you'll find out that these two numbers are awfully similar. The tangent of an angle, if that angle is really small, is approximately equal to the radian measure of that angle itself. So that's the reason that this ends up being so close together. That for really, really tiny angles, the angle measure itself and the tangent of that angle are almost the same number. They're very close. They're only off by, well, some small factor. It's on the order of the cube of that angle.